Hello everyone, today I'll talk about radiation protection procedures in nuclear medicine. Our outlines there: number one, radioactive transportation and receiving shipment. Number two, radiation protection in the hot lab. Number three, safe administration of radiopharmaceuticals. Four, radioactive spillage decontamination. Number five, radioactive waste management. Number one, radioactive transportation and receiving shipment. If we are talking about any radioactive material, so you have to know at the beginning that in radioactive material, consider as a radioactive material if it's a specific activity greater than 0.002 microcurie per gram. It means 74 becquerel per gram. For the vehicle which containing radioactive material, 3 place cards on vehicle should be there at different places to give indication that there is radioactivity inside the vehicle. All regulations, you can find it easily in safe transport of radioactive material in IAEA safety standard SSR 6. Transportation of dangerous goods, class 7 shipping. In radioactive material, it's under class 7. So you will find here the radioactive material under class or under category class 7. So we have different radioactive material levels. We have 3 radioactive material levels: level 1, level 2, level 3. Here in our nuclear medicine, most common radioactive sources used in nuclear medicine department under radioactive level 2. As you can see here, for receiving shipment of radioactive material, you have to follow the following procedure: wearing gloves, visually inspect the package, measure exposure rate at the surface and at 1 meter from the radioactive package. You have to do wipe test, packing slip, inspect inner shielding container, discard the package, and record all measurements you did it. You have to wear gloves and you have to wear double gloves, okay, to protect your hands from any contamination. You have to inspect the package itself if there is any cracks or damage. You have to measure the exposure rate at the surface and at 1 meter from the radiation package. That's important using your radiation survey meter, which is calibrated well and which is checked every day by measuring the radiation background and using standard radioactive source to check the radiation to check that the radiation survey meter is working properly. Here, during the procedure of receiving shipment, you have to check the radiation level at the surface of radiation package and at 1 meter from the radiation package. After that, you have to do the wipe test. This wipe test using certain cotton or a certain tissue. This tissue, you have to do wipe test like that, okay, and you have to scan a certain area. This area is around 300 centimeters square. The count rate should not exceed 220 disintegration per minute or count per minute per centimeter square. So here you have to multiply 220 disintegration per minute per centimeter square times 300 centimeters square, which is the area you are concerned with, or the area of this cotton. Okay, so this is the area of the cotton you are using it for wiping, multiplied by the efficiency factor, multiplied by the conversion factor from count per minute to disintegration per minute, which is 0.19. So at that time you will get the value 1254 count per minute. So the wipe test at the surface of the package or the inner side of the container or the surface of the container itself should not exceed 1254 count per minute. That's in case you are using survey meter for measuring the dose or the measuring the radiation level in wipe test. But if you are using well counter for that purpose, so at that time you will remove the factor of conversion from count per minute to disintegration per minute, and using the same equation you will get the value 6600 count per minute. After doing the wipe test, you have to inspect the inner shell of the container if there's any cracks or any damage. After that, you have to remove the label of radiation sign and discard the package as a normal waste. You have to check all shipping papers, okay, and you have to check the name of the radioactive material, and you have to check the activity, and you have to check the United Nations numbers. There is something which is important, which is called transport index. This transport index, which is written in the radiation label, which is equal to the maximum dose rate at 1 meter in microsievert per hour over 10. Here there are different labels. Each label, okay, which give you indication about the radiation or the radiation level at the surface of the container and at 1 meter. Here, this white label, you will find here the radiation level at the surface of the container is 5 microsievert per hour, while the radiation level at 1 meter is should be less than 0.05 microsievert per hour. Here the transport index Ti is equal to 0. While if you are using yellow 2 label, so at that time the radiation level at the surface is greater than 5 microsievert per hour up to 500 microsievert per hour, while the radiation exposure at 1 meter should be less than 10 microsievert per hour, and transport index should be from 0 up to 1. As you can see here, the radioactive 2, that's mean low level of radioactivity. Here's the contents: is cesium 137. The activity is 0.37 gigabecquerel, which is equal to 10 millicurie. 0.8 here is the transport index, and 7 here is the class 7. I mentioned it before. Yellow 3, here the radiation exposure at the surface is above 500 microsievert but less than 2000 microsievert per hour. And the radiation exposure at 1 meter here from range 10 microsievert per hour up to 100 microsievert per hour, and transport index here from 1 to 10. Most common radioactive source used in nuclear medicine department used here in yellow 2 label, class 7, type A package. Here you will find also some numbers you have to know about it. United Nations 2915 means radioactive material type A package, non-special form, non-fissile or fissile expected. And also we'll find type A packages used to transport small quantities of radioactive material with higher concentrations of radioactivity than those shipped in industrial packaging. So you have to take care about type A and United Nations number. For the wipe test used for gamma or beta source, as I mentioned before, 220 disintegration per minute is the limit for gamma radioactive sources, but in case of gamma or beta, 220 disintegration per minute. But in case of using radioactive sources which emit alpha particle, 22 disintegration per minute is the limit for the wipe test. As you can see here, back at the receiving shipment test, here this is our package which containing radioactive material. Okay, so after receiving the radioactive material, you have to check the radioactive material inside. Here we have to check after checking the documentation and to make sure that the paper and the order activity is one which is received. We are using our radiation survey meter which is calibrated, and you have to check the calibration date. Here we are measuring, or we are checking the radiation survey meter using internal radioactive source standard source. Here we are starting to measure the radiation exposure at 1 meter, and to check the radiation should be less than the limits of radiation exposure at 1 meter and at the surface of the package itself. Here he is checking the radioactivity or the radiation exposure at the surface of the package. If it's okay, at that time we are doing the wipe test to check the contamination or the radiation contamination at the surface of the package itself. I'm just only selecting the 3 places, one outside the container and the inner side and at the inside the lead shield itself. After that we bought the the wipe tissue inside the container itself and to get the reading, which has which is which should be less than 1245 count per minute. After that, we are recording all measures. We did it. Check all papers of shipment, pass or not pass. Physically check of the package if there is any damage or not, pass. Reading at 1 meter, so we have to check the reading at 1 meter from the package. Reading and the surface should be less than, at 1 meter should be less than 10 microsievert per hour if we're talking about type 2 or radioactive type 2. Here it should be less than 500 microsievert per hour. We have to check the label and transport index, yellow 2 type A, United Nations 2915 and class 7. For the white test and the surface of the package, here we are doing should be less than 1254 count per centimeter square. Here wipe test at the surface of the container. Here wipe test of the inner side of the package itself. So we have 3 wipe tests we have to do it at the surface of the package, inner side of the package, and surface of the container. Surface of the container itself, which including the radioactive material. Let's move to the second point, which is which talk about radiation protection in the hot lab. In the hot lab, we are dealing with radioactive material inside, so the door itself, you have to find radiation signs outside the door to prevent smoking, drinking, eating, and also you will find local rules how to behave in case of radiation spillage, in case of fire, in case of emergency. All these local rules should be hanged inside the hot lab and should be followed in case of different scenarios. So now in the hot lab, we are dealing with radioactive material, so we have to protect ourselves and to protect our hands, and we have to protect ourselves from radiation spillage. So that's why when dealing with radioactive material, we have to put the radioactive material in the proper shell. So we have to use shield vials, which composed of or manufactured by with lead or tungsten material. A selection of the proper material based on the type of radioactive source. Normally we are using tungsten for F18 while using lead material for technetium 99M, while using perspex material for radioactive or for beta emitter radioactive sources like yttrium 90, like yttrium 90 or lutetium 177. Okay, we have to use protective clothing, like as you can see here, he's wearing aprons and overshoes and also overhead here to protect himself from any spillage. It might happen because spillage, radiation contamination, spillage radioactive is happening every day in nuclear medicine department. Also, we have to use tools for remote handling of radioactive materials because direct contact to the radioactive material is not allowed. We have to use forceps for source distancing, and at the same time these forceps also is important, is mandatory in case of using beta source radioactive material. Containers for radioactive waste, also we have to use waste or bin, lead line for the waste, for sharps, for syringe, for vials. Also inside the hot lab you have to use area monitors or dose rate monitor to check the background radiation inside, and if it exceeds a certain limit like 10 microsievert per hour, give you alarm that there is any spillage or is there is a high radiation level which is not allowed there. Contamination monitor, as I informed you before, we have to use the radiation thermometer for that purpose. Decontamination kit, that's very important. We have to use kit which including radio wash, absorbent paper, absorbent sheets, and radiation signs. Gloves, overshoes, all these should be there beside the hot lab in case of emergency. In case of spillage, we have to use it, which has to be very near to the hot lab to be used in case of radiation spillage. Signs, labels, record. That's important to record everything, including radioactive material going to be used inside the department, and also labels for any radioactive material after preparation should be labeled under using certain activity, certain activity and type of radioactive material. Signs also should be used everywhere inside on the top of the waste bin, on the top of the storage bin, and on top of the doors, everywhere. For also if you have a store for calibration sources should be used, so signs should be everywhere to give you a to be like alarm or to warn that there is radiation or this area containing radioactive material. As informed shielding, here we have syringe shield used for syringe, okay, and also shield vials used for containing vials containing radioactive material. Syringe shield is composed of or manufactured by lead or tungsten or perspex as well. Here also you can use structure shielding like that, okay, which is manufactured by lead glass. Lead glass enables the radiation worker to monitor the radiation underneath, and at the same time protect or prevent the radiation going out or received by the patient by the worker body. Okay, forceps, as I informed you, used for source distancing to avoid radiation exposure to the hands of the radiation worker, especially used for beta source radioactive material. Here, Borsen zometer, this ring zometer used for radiation exposure to the hand. This one used for TLD badge or film badge, used for whole body radiation exposure determination. Here's this one used for radiation contamination, and also we can use radiation area monitor to detect the radiation background or radiation level in the rooms, in scanning room or in the hot lab. Here also, as you can see, radiation label, okay, to type the name of the radioactive material, name of the radio-pharmaceutical, the time, volume, activity, concentration, date, everything regarding the radioactive material used before administration. And also we have to use this table and the records and mentioning the technetium generator or the radioactive material serial number and reference activity and reference date. You can use this one for that purpose. Also, emergency kit should be kept readily available and near to the hot lab, including protective clothing, overshoes, gloves, decontamination material for the affected areas, including absorbent material for wiping up spills, decontamination material for person, warning notices, that's important. Also, in case of spillage, portable monitoring equipment, bags for waste, that's important because after cleaning or after spillage, we have to put the the contaminant or the absorbent sheets and label and pin. If you are using anything for cleaning at that time, we have to discard it in a certain bags. These bags, after that, we have to measure it and put it in the waste bin. The most important thing in our hot lab, we are using radioactive material coming in generator form. The generator containing molybdenum, which is eluted every day to produce technetium-99, and this technetium-99 come up here in the shield vial, in this evacuated vial collected here. So now this you will find here two opening, one used for saline, another one used for withdrawing the technetium using evacuated vial. So all this molybdenum, this generator already is very heavy because it contains a lot of lead material. This lead material used for to prevent the radiation coming out from the generator itself. But this what we have in nuclear department, maybe one generator, two generator, or three generator, and so that's why we have to use a store cabinet for that one, for the generators. After receiving generator, we have to store it in a proper place, and we have to make sure that the radiation exposure coming out from the generator is under the permissible exposure level. That's why we are using laminar flow cabinet. As you can see, laminar flows cabinet here, you will find here on the left side here, this place, a proper place for generators, and the other side here, this is another place for waste bin, which used to collect the sharps, to collect the syringe, and here this one is used for to store one to four generators, and this one is lead lined with a proper thickness to prevent the radiation to go out and to expose the radiation worker. Also here you can see the waste collection, and this also is composed of bin which is lead lined with a proper thickness for shielding purpose. Okay, so now if you have a vial of containing radioactive material like thallium, technetium, or F18, so if you measure the exposure coming out from 1 megabecquerel at 1 meter from thallium, it will be 0.01 microsievert per hour, while 0.02 microsievert per hour for technetium, while 0.14 microsievert per hour for F18. All of them have the same activity at the same distance, but different radioactive sources, that means different energies. So F18 now give you higher radiation exposure because it has a higher energy, and at the same time it has a higher dose rate. Why? Because it has a short half-life. Here is the exposure coming out from F18, because nowadays we are using FDG for PET-CT imaging, so you have to be careful about that, because the radiation exposure for hands, in case you are using syringe containing only single dose of FDG, it will be around 7,000 microsievert per hour in case of no shielding used for that. But in case of using shielding, the radiation exposure will be less than 150 microsievert per hour. So shielding is a mandatory to protect your hands and to protect your body from the radiation exposure coming out from F18. You'll find the difference here from 7,000 to 150, which is very big. So you have to keep the dose to hands at an acceptable level. That's why we are using syringe shield. Syringe shield manufactured by a certain material. This material with a high density material, especially if you are using it for FDG, so it's properly used. Tungsten, which has a high density and high densities, so we can use less thickness or lower thickness than lead for shielding purpose. Here, if you are dealing with yttrium-90 or beta emitters like yttrium-90 or lutetium, so at that time you have to use perspex material. Perspex material will prevent the beta particles to go out and prevent Bremsstrahlung or limiting Bremsstrahlung production. But if you are going to use lead material, so lead will interact with beta particle and will cause Bremsstrahlung radiation. So it's recommended to use perspex or proper plastic shielding should be used to absorb beta particles or beta radiation sources. Also, any shielding vial or syringe shell should be you have to find their lead glass. There's a lead glass enable you to monitor the volume or the liquid inside or the radioactivity inside, and at the same time prevent the radiation to go out to protect you. Source distancing, as I mentioned before, that's mandatory in case of using beta radioactive sources. You have to keep the sources shielded as much as you can during handling or administration or fractionation of the dose. Here, as you can see, different radioactive sources used, and you'll find here specific gamma ray constant. You will have to put it in your mind. You have to know the specific gamma ray constant, which give you information about the radiation exposure at 1 meter from 1 megabecquerel of different radioactive sources. So now you have to know the half value layer for different radioactive sources and 10th value layer for different radioactive sources. This information is very important for shielding purpose. If you are going to use or to calculate the shielding is the thickness, the proper thickness for shielding F18 or lutetium or technetium. So you have to know the 10th value layer, half value layer, and specific gamma ray constants. For example, here, if you have a source of technetium containing 30 gigabecquerel, so the activity is 30 gigabecquerel, and the dose rate at 1 meter should be 2 microsieverts. So I want to know what is the proper thickness to reduce the dose rate to 2 microsieverts per hour. So I want to reduce the dose rate to 2 microsieverts per hour. So I have to know the first, without shielding, what is the dose rate of 30 gigabecquerel of technetium 99? So using a specific gamma ray constant, dose rate constant, which is 0.021 microsievert per hour. So you have to multiply these values. This is only for 1 megabecquerel. So gigabecquerel is 30 gigabecquerel, so it's around 30,000 megabecquerel. So by multiplying 30,000 megabecquerel by the dose rate coming from 1 megabecquerel, so you will calculate easily the dose rate from unshielded, or the whole amount of 30 gigabecquerel, which is 630 microsievert per hour. So now we know the total dose rate for unshielded source of technetium 99. I want to reduce this value to 2 microsieverts. So I want to know how many times the reduction. It will be 630 over 2, so it will be 315 times, which equal, by this equation, which is very easy to get it, logarithm of 315 over logarithm of 10. 10 here indicate the 10th value layer, so you will get 2.4 10th value layer, which is equal to 2.5 millimeter of lead. By knowing 10th value layer, okay, so you have to multiply 10th value layer by 2.4, it will give you 2.5 millimeter lead. From where we get this equation, it's easy to be calculated as follows. If you want to know the dose rate coming out during or by using 13 thickness of x, so you have to know the original dose rate over 2 to power n. N here is the number of half value layer. So if I want to calculate the x, you have to 10 to power n. N here is the number of 10th value layer. Okay, so using this equation, can get easily the dose rate using the proper thickness of any material. By knowing the half value layer, you can use this one. By knowing the 10th value layer, you can use this one. Okay, safe administration of radiopharmaceutical. If you are after preparation using chilling vial, using and you are fractionating the dose, or you are using a certain dose, so now you have to put this syringe containing a certain amount of radioactivity in a syringe shield. Why? For administration. Syringe shield will protect your hand from radiation exposure, your body from the radiation exposure. As you know that we given the dose, or we administer the dose orally or intra-injection. Sometimes we can use intra-articular also, or body cavity. That's important to know the procedure and to know how to protect yourself and your hands from the radiation exposure. That's why we are using the syringe shield for that purpose, and we are using syringe carrier to put the syringe shield inside for moving the dose from the hot lab to the injection area. Here, during the administration procedure, you have to wear gloves. You have to put here also absorbent sheet under the cannula. Why? Because this will help us to absorb any drops coming out from the cannula. In case it happens, it will absorb and prevent any patient contamination, patient radiation contamination. You have to use this syringe shield for injection. So we have to do and train the staff how to do that in case of using non-radioactive material. So we have to do that without radioactive material at the beginning, using water, using any non-radioactive material to break the fear, or to avoid any worry might happen for all radiation worker inside the nuclear medicine department. Here, as you can see here, the radiation exposure coming out from the syringe, okay, without shield and with shield. The radiation exposure here, it will find at the tip 6 millisieverts per hour, while here is 8 millisieverts per hour at the tip of the syringe. So here 22 millisieverts per hour at this point, while here is 0.16. Why? Because it's shielded. This is shielded with 2 millimeter uh, lead. So now, if you have a syringe which containing 400 megabecquerel of 99 technetium in 1 ml, so at that time you have to know very well that using cell shield will protect your hand from radiation exposure, and the difference between 22 millisievert to 0.16 is very big, so you have to use the syringe shield to protect your hand from the radiation exposure. Also, we have to use a proper syringe shield used manufactured by from Perspex in case of using beta source radioactive material. Okay, so now in compare, if we want to compare the radiation exposure coming out from point source, vial, the patient himself, at the administration, and the patient himself at time of examination. Okay, the radiation exposure or the radiation coming out from the point source vial for different radioactive material for F18 and technetium, you will find that technetium here give you radiation exposure is around 261 microsievert per hour per gigabecquerel in case of using point source, but in vial 22 microsievert per hour. From the patient, 10 microsievert per hour in case of administration during the administration procedure, but for examination you will find the radiation is 8 microsievert per hour. While F18, the radiation exposure will be very high, which is 18010 at 0.3 meter from point source and 163 at 1 meter from point source. In case of using vial, 158 microsievert per hour. From the patient during the administration process, it's 92, and at the time of examination is 62 microsievert per hour. This in case you are using point source, vial of radioactive material, the patient during administration and the patient during examination. But in case you are using the radioactive material for preparation or administration or examination, so at that time you will find the radiation exposure coming out from F18 in case of preparation. It's from 0.6 up to 2.7, but for administration from 3.7, 6.8, for examination from 3 to 12. So that's mean examination procedure give you a high radiation exposure if you are using F18 source of radioactive material. But in case of using technetium during the preparation is 1 microsievert, administration 0.5, examination 5.5. Finger dose. Here, if we are concerned with the finger dose, what is the dose received from F18 and technetium. Also, F18 will give your finger higher dose than technetium 99M. So you have to be careful about that. Using syringe, using vial containing F18 will give your hand and your finger too much dose incomparable with technetium 99M. Also during preparation and administration, which one give you higher dose? Preparation give you higher dose because at that time we are using the total amount of radioactive. We are during the preparation we are staying long time during fractionation and withdrawing the dose, so it gives your hand or your finger higher dose. But during the administration you are fast as much as you can, so the exposure time is less, so the radiation exposure here is lower during the administration incomparable with preparation. That's in case F18 and technetium 99M as well. Fast, that's why I'm telling you have to be fast as much as you can and train staff to undergo a period of intense training in which they practice manipulation using non-radioactive liquid prior to undertaking any dispensing of radioactive liquid. Okay, It's recommended to use also automatic injector, which reduce the radiation exposure. Here you are using the automatic injector, which is, I think, the most common one is Carl 100. Carl 100 is the most common radioactive material which is used here, but we are using here a special technique for dispensing the radioactive dose per patient. So at that time, we have to prepare the dose for each patient, which take around 5 to 10 minutes for preparation, and at the beginning, at the morning, around 20 minutes for calibration. So at that time, we are using this injector, okay, and remove it, and we are connecting this device with to the patient, and it's used for automatic injection. So this one is lead shielded, so it will reduce the radiation exposure to the radiation worker. As you can see here, using syringe shield and lead container, the radiation exposure to the whole body, it will be 7.5 microsievert per hour, microsievert per gigabecquerel. While using automatic dispenser, it will reduce to 4.5 microsievert per gigabecquerel. Okay, so now we talk about the automatic injector, but now we will talk about the apron. Lead apron. Lead apron, it's mandatory to be used in X-ray, because in X-ray we are using polyenergetic X-ray. So the average dose or the average X-ray energy is 1/2 to 1/3 the maximum energy. So in case you are using in X-ray 120 kV, so you will find the energy is around 42 or it's around 70 kV. So now 70 kV, so the interaction happen between the X-ray photon and the lead apron is the dominant interaction is photoelectric effect, so complete attenuation will be happening to the X-ray photon. That's why you will find the lead apron is a mandatory in X-ray or cath lab or CT. Why? Because it will reduce the exposure by 99%. While here in nuclear medicine, we are dealing with radioactive sources, which is monoenergetic, and the radiation energy is high, maybe greater than maybe 140 kiloelectron volt for technetium and 511 kiloelectron volt for F18. So the most common, so the dominant interaction here will be the Compton scattering. So the reduction in the radiation intensity received by the worker body will not be too much. So as you can see here from this curve, so if you are comparing, if you want to see the radiation exposure reduction in case of technetium 99M, you will find here the reduction is around 60%. While using lead apron, in case of F18, the reduction here it will be around 8.9%. So when the radiation energy increase or the radioactive source energy increase, that time the reduction in the dose reduction received by the radiation worker will be more or less. So here, if you are comparing F18, technetium, iodine-131, yttrium, gallium, you will find here the dose reduction here in F18 is around 16.8, while in technetium is 64.5. In iodine-131 is around 3. So you have to take this in your consideration. Okay, so if you are if you're able to increase the lead thickness, so at that time you will decrease the dose received by radiation worker more and more, but it will be very heavy. Okay, you will not be able to carry the lead apron at that time. Okay, so let's move to another point, radioactive spillage decontamination. It's important because radioactive spillage might happen every day, and the probability of radiation spillage is high in nuclear medicine department. Radiation spillage might happen because in case of preparation, you can spill might happen during the preparation, as you can see. So you have to know how to deal with this spillage, and all this should be hanged and should be there in the hot lab, and the procedure should be known and should be trained to everyone working with radioactive sources, for nurses, for radiation technologists as well. As you can see here in this video, okay, here we have a patient. Okay, so we are going now to inject the patient with radioactive material, and this is the radioactive material which is spilled now on the floor. Okay, can you see now what is the proper action will be happened by this technologist. Now he is telling the patient, don't be panic, be calm, don't worry, okay, and he will start to throw this absorbent sheet on the radioactive material, as you can see. Okay, so he will evacuate the room and he will tell the patient, please go out, and he will make a call for the radiation safety officer. We have a spillage. The radiation safety officer will come and will wear gloves, wear protective clothes to start the contamination process. So at that time, as you can see here, he will he will wear the shoes over and gown, gloves, double gloves, the mandatory. She has to confine the area of the radiation spillage at the beginning. Confining the area, okay, Marilyn spreads less than 40 megabecquerel, as you can see. So now she is going to check also the technologies if any spillage happen or any drops happen or thrown, and also check the patient if there is any radiation on her clothes, okay, and after that, he will evacuate the place from the technologist and the patient, and you will start to confine the area and determine exactly the area of the contamination using this tab. Confining the area is very important to know where exactly the radiation spillage happened. Okay, after confining the area, he will start to clean or start to clean from outside to inside. Don't try to clean from inside to outside, as you can see. So after that, using this radiation or this powder, which has ability to attach the radioactive material, and after that, using absorbent paper again. Sometimes using radio wash or a certain powder for that purpose. It's available. You can use it. As you can see, from outside to inside, the cleaning from outside to inside. Don't try to spread over. And now, after you satisfied about the cleaning procedure, you will measure again. If it's background, it's okay. If it's higher, still higher, you have to clean again. The background now is 5 microsievert per hour. If it's still high, you have to clean again, or you have to use this radiation sign to prevent anyone to come to this area. If the radiation level is high, and you can close the room which containing radioactive material for a certain time and check again. It depends on the type of radioactivity which is spilled already on the floor. Now, after finishing, she is checking the radiation contamination on her hand and shoes, and sometimes using foot hand contamination detector to detect the radiation level. Okay, so now the radiation contamination 5 times greater than the background radiation. Store the radiation waste to 10 times half-life. Keep in mind allow as low as reasonably achievable time distance shielding. Okay, decontamination procedure, we have a small amount of radioactivity spillage or larger amount. In case of a spillage of small amount could be removed easily, like a spot of blood, like a small amount of drops of liquid but there is no large amount of radioactivity. Doesn't give high external hot dose, but in case of large amount could not be removed easily, could give high external body dose. The goal of decontamination procedure is to reduce the dose to the person. The person includes also person involved with the decontamination procedure. So in some cases, such as with short-lived radionuclides, it can be simpler to quarantine the area for a sufficient time to allow, oh yes, this is important, you have to do that. And sometimes the radiation level is very high, you can isolate and you close this room for some time, okay, to allow for decay. After that, you can allow any person to go inside. Okay, first of all, You have to be calm, react with order, try to avoid any spread of the contamination, ask help for colleague as soon as possible. You have to call the radiation safety officer, wash your hand as soon as possible following your operating procedure. Water and soap are enough for cleaning your hands. Wash carefully around your fingernail. Don't use abrasives. That's important. You use brush techniques, and because this will cause entering the radioactive material inside your skin. So don't use brush for that. You should have a copy of the operating instruction. Oh yes, that's important to make a standard operating procedure for radioactive decontamination and train people how to use it and how to check it. Okay, this is the food hand contamination detector, which can be used. You can here you both your hands and here you both your feet, and this one can be used also to check your clothes. Okay, or you can use this pancake GM counter, can be used as low as cost alternative to the food hand contamination detector. This one is called food hand contamination detector, and to check the radiation level here, there is an option to select the type of radioisotope which you are concerned with, if it's iodine, technetium, or F18. Okay. Also, in case of personal contamination, if there is any spillage happen to yourself, so at that time you have to take off your clothes and you have to put it in a certain bag, and this bag should be measured and should be recorded, and you should write the date, right time, right the dose rate at this level, and you have to keep it for a certain time. It might be a 10 half-life or short half-life radioisotopes, and at that time you have to measure it again, okay, to check if it's background or not. If it's background, you have to scar it as a normal waste. You shower is a mandatory in the hot lab for person decontamination. In case of radiation spillage happen to your body, so at that time you need a shower to remove the radiation or the radiation drops or radiation contamination happen to your body. And also we are using sink to use water and soap for hand contamination, which might happen. Okay, and at that time you just only open the tap and use water. Don't try to touch anything at that time, but just only let the water move, okay, rapidly on your hand, and it will remove the drops of radioactive material to the sink. You'll find the contamination kit which has to be near to the hot lab, and at that time you will find the gloves, absorbent sheets, decontamination solution was spread, sometimes using radio wash, plastic sheets, and tap bags to hold the contaminated items as well, like this one. This contamination kit, which commonly used nowadays, is a radio wash solution and radiation notice also to prevent anyone to go inside. In case of small amounts of radioactive material, low volumes of non-toxic radiopharmaceutical can easily be removed, such as up to 10 megabecquerel of F18 or technetium-99m. The following action should be taken. Number 1. Use protective clothing and disposable gloves. Quickly upload the spill with an absorbent pad to prevent it spreading. Remove the pad from the spill and dispose of it. Wipe with a tissue or proper towel from the edge of the contaminated area towards the center, from outside to inside. Monitor the paper towel. You have to monitor the paper after using it, also using the radiation survey meter for residual activity, for example, using contamination monitor or performing wipe test. You can also use or do wipe test to check the radiation inside. You can use wipe test, or can do wipe test several times to check the radiation level for the spillage area. Continue cycle of cleaning and monitoring until the measurement indicates the spill has been removed, and try to keep the volume of contaminated waste as small as possible. Use a plastic bag to hold the contaminated items. Suitable bags and paper towels should be readily available. If the decontamination process is not successful, contact the radiation protection officer. Monitor all people involved in the spill you should do that. You should monitor all people involved in the spill for contamination when leaving the room. In particular, monitor shoes if the spill is on the floor. Spillage of large amounts of radioactive material at that time, for example, if the patient undergoing iodine 131 therapy, which is commonly happen for patient vomit shortly after administration, the following action should be taken: throw absorbent pads over the spill to prevent further spread of contamination, evacuate people not involved in the spill from the area immediately, inform the RPO immediately, and conduct cleanup under his or her direct supervision, monitor all people involved in the spill for contamination when leaving the room if necessary, perform thyroid biopsy of all people involved. If clothing is contaminated, remove it and place it in a plastic bag labeled radioactive. If contamination of the skin occur, wash the area immediately. If contamination of the eye occur, flush with large quantities of water. When the contamination is contained, the procedure outlined for cleaning small spills may be followed with particular care that the contaminated waste bags are appropriately labeled and stored. Restrict the entry to the contaminated area until decontamination has been completed and the area has been released by the RPO. As you can see here, we are using sometimes this marker for confining the area of contamination. That's important. You can use tab, you can use this marker for that purpose. In case of wound, you have to be careful during the cleaning of radioactive of your hand during radioactive contamination to be sure that the radioactive material not going inside the wound. You have to be careful about that. Also using water, soap, that's enough, or only water, just only to remove the radiation from the contaminated area. Here, if there is any contamination to the nurse hand, at that time the nurse hand contaminated with radioactive material was F18, which was around 15 kilobecquerel per centimeter square. So at that time, we are the limit of detectability of contamination is 30 becquerel per centimeter square. This is the level of contamination. So below 30 becquerel per centimeter square is accepted, but above this value there is contamination. Okay, so this is the value of this is the limit of detectability of contamination. So if you want to estimate the skin dose, if your hand contaminated with 50 and the reading is 15 kilobecquerel per centimeter square, you have to multiply this value, okay, by the specific memory constant, okay, for the type of radioactive source, which is F18, multiplied by the time of exposure, which is half an hour. So at that time, your hand you will receive 14 millisievert. Okay, for contamination or for spillage or for cleaning purpose, at that time, floor should be finished in an impermeable material which is easy to clean and resistant to chemical damage, curved to the walls, as you can see here, curvature, okay, to prevent any entrance of radioactive drops inside the floor or between the floor and the wall itself. It should be finished in smooth and washable surface, for example, painted with washable non-porous paint. That's important. No pores or no pores inside the wall, which might absorb, which might permit to might allow for the radioactive material to enter inside. Okay, let's talk about radioactive waste management. The waste coming out from nuclear medicine department, we have injection room, dispensing laboratory, hot lab, gamma camera rooms, waiting rooms. We have liquid waste, solid waste, gaseous waste. For solid waste, it's like sharps, vials, syringe, okay, which has to be stored in lead containers or lead bin, which and should be measured, okay, after reach the 2/3 of the level of fall. Okay, at that time we have to measure if it above the background. So at that time we have to store it in the waste room Okay, based on the time, based on the radioactive source type, so it will be stored in half-life. So at that time we will measure the dose rate and we will store it for some time to make sure that the radiation level is below 5 microsieverts per hour, which is the background level of radiation. That's in case we are using solid waste, but in case we are dealing with liquid waste, okay, and gaseous waste, so we'll talk about this one now. Okay, so procedure for collection of radioactive waste collected from all collection areas, okay, and we have two methods, activity-based method, okay, mainly for capsule and use vials, okay, if the activity less than 111 megabecquerel, 3 millicurie stored in the storage cupboard for 10 half-lives. If the activity above 111 megabecquerel, 3 millicurie stored in the storage cupboard for 20 half-lives. Okay, but dose rate method you have to measure. This is only for syringe or other contaminated items because you cannot measure each item. So that's why we are using dose rate method. But in case of vial or capsule, you have to use activity-based method. Okay, because you can measure it using dose calculator. You can measure the capsule and the vial itself. It's less than 111 megabecquerel, so at that time you can store it for 10 half-life. If it's above 111 megabecquerel, above 3 millicurie, you can store it for 20 half-lives. But for dose rate method, you have to use it for syringe or other contaminated items. Measure dose rate at the surface. Dose rate if it's less than 5 microsievert. So now put in the cleared radioactive waste area and let domestic staff dispose of them as a non-radioactive, as an ordinary waste or normal waste. If it's a dose rate less than 5 microsieverts per hour. If the dose rate greater than 5 microsieverts per hour, store item in a storage cupboard in the radiopharmaceutical laboratory till decaying to 5 microsieverts per hour. And we have to record that, and we have to use radiation label like that. And we have to write the date, time, the dose rate at that time, and signature. Okay, so by time, and you measure it maybe after a week or after 2 weeks, and measure it again to make sure that the radiation level less than 5 microsievert per hour. At that time, you have to discard it as a normal waste. Okay, areas of collection, you can assign a certain room for waste room, or in the hot lab if you have waste cabinet, okay, used for segregation of you can find sharp container like that. You can find bags, certain bags, or waste bin like that. Okay, so there are different forms and different containers based on the type of radioactive source. So if you are using sharps, you will find container for sharps like that one. You can find another container for vials and syringe also. You can assign a certain container for short half-life, other container for long half-life, and also you can use a certain container for non-radioactive sources. Okay, so now here also we can summarize what we mentioned before for short, medium, long half-life. Okay, if you know the radioactive source and you know its half-life, so it will, what is the whole time for each radioactive source in case of short, less than 7-hour half-life, so you can hold it for 2.5 days. For example, technetium-99m. For 7 to 4 days, like iodine or yttrium or indium 111, so you can hold it for 33 days. For long half-life, 8 days plus, so you can hold it for 67 days or 81 days or 111, depends on 67 days for lutetium 177 or iodine 81, which is around in half-life. For 114 for radon 223, which is around 10 half-life for Silver's half-life up to 120 days. This container used for sharps, and this container used for radioactive waste, for normal waste, not for radioactive waste, for radio contaminated items, and you can use it for syringe, vial, and this one dedicated only for sharps. And heavy shielded for large volume bit waste, especially for your bit, because in bit you have to be careful about the proper thickness used for F18 because it will be higher than technetium. Normally for technetium you can use 4 millimeters, it's okay, but for technetium, for F18 you have to be careful about that because we have to use tungsten or higher thickness of lead material. Okay, these are different shapes and different container used for waste. Okay, so now for this what I mentioned before, it was for solid waste, but now we are talking about gaseous waste. Gaseous waste, if the activity is within the limit less than 3.7 kilobecquerel per meter per cubic meter, so now gas released into atmosphere, no worries about that. But if it exceeds the limit greater than 37 megabecquerel per cubic meter, use air filtration system and release through the atoll effect. That's why we are using fume hood or laminar flow for that purpose. And regular environment survey should be happen, and you can take a white test or you can use filter to check the radiation. You can use filter inside the host itself, in the hoster itself. You can use a filter to check the radiation level inside it. The most important thing here, in case we are dealing with liquid waste. For gaseous waste, we mentioned it already. For laminar flow or fume hood used, which is automatically used for by ventilation system to remove the radiation vapor or the vapor, the radioactive vapors outside our department. But here in liquid waste, if we have iodine rooms and we have a patient and we have a toilet, hot toilets, these hot toilets, the patient going to void before doing the scan. So some amount of radioactive material will go inside our toilets. So we'll go to the main sewage. So at that time, we have to make sure that the activity going to the main sewage is less than the annual limit intake. Here in Federal Authority of Nuclear Energy Funnel should be less than 10 becquerel per milliliter. So that's why we are using a special tank or tank decay system. This tank decay system, all toilets, all hot toilets should be connected together to the tank decay system. Okay, so at that time, the tank decay system used to decay or to store the excreta, the urine and stool for a certain time for decay purpose. As you can see here, this is a tank. Okay, this is a toilet, hot toilet connected to the tank. Here you can find different tanks, and one for collection and another tanks for decay. So as you can see here, this one for collection to collecting. So all toilets, okay, all toilets content will be collected here in tank number one. So after that will be bumped to tank number two and three for decay. So after that, and we have to check the radiation concentration activity to be less than 10 becquerel per milliliter. So at that time, we have to bomb it to the main sewage. So that's important and mandatory in case of using iodine 131, especially for iodine 131, long half-life radioactive source in isolation room for therapy. But for short half-life, it's not a mandatory. But for long half-life iodine 131, it's a mandatory to be used for reducing the concentration activity and before release to the main sewage. Tank decay system calculation is a complicated procedure. You can follow IEA, International Atomic Energy Agency, Technical Enhanced Document 1417. Okay, to check the procedure and the calculation, how to calculate the tank decay system or decay tank system for that purpose. Okay, as I informed you before here, this one for collection. So after that, it's pumped to this one is called collection tank. So it's pumped to the decay tank number 2 and 3 and 4. This for decay. So after that, you have to monitor the concentration activity. It's less than the annual limit intake or the concentration activity, the allowed concentration activity. It will be pumped to the main sewage. So that's why you will find all toilets and sinks, okay, already stainless steel line to prevent any attachment of radioactive material with the walls and sink itself, and this will reduce the contamination probability of radioactive material. So here, if you have a toilet like that, another toilet, all of them connected to tanks, one for the collection tank and another one for collection tanks to hold the radioactive material for a certain time for decay. Radioactive waste report, you have to do waste report. Okay, as you can see here, we are using the waste coming out from the hot lab, from injection rooms, from PET-CT, from SPECT-CT room, collection tank, decay tank, and we have to measure the initial dose rate and final dose rate before release as a normal waste. And we have to write the date of the initial dose rate and the date of release date. Thank you so much for your time. Thank you for your attention. If you have any questions, please let me know. Thank you so much.